In this lesson, we will introduce the idea of a polar coordinate system. Let's start by reviewing some trigonometry. Under this introduction question, it says, given the following figure, is it possible to find an equation that we can use to find the values of x and y? Seems to be a typo here because it's an equation. For values of x and y, where x and y is just a coordinate point. Well, in any coordinate point, we can always draw a right triangle where one of the vertex is going to be that coordinate point that we want to find an equation of. And let's assume that this is my reference angle. Well, if that is my reference angle and we do have a right triangle, then we can definitely use our trig identities, where the sine of any angle, recall from SOHCAHTOA, that sine is opposite over hypotenuse. But if this is going to be my reference angle, then y is my opposite, r is my hypotenuse, and x is my adjacent, given this right triangle. So therefore, the sine of my reference angle, it's opposite over hypotenuse, which in this case, the opposite is y, and the hypotenuse is the value of r, which we already stated, that that's just the distance from the origin to the point. And now notice that we have this simple equation right here. If we multiply r to both sides, now we have an equation for y. So now we know that y is equal to r times the sine of that reference angle. So here we have a simple equation which we can use to figure out the y coordinate or the y value of my coordinate point. And I notice that if we would have taken the cosine of this angle, which again cosine is adjacent over hypotenuse, where right now my adjacent is x and my hypotenuse is r. Notice that if I want to solve for x now, if I multiply r to both sides, that cancels out. So now I know that x is equivalent to r times the cosine of theta. So here we have two simple equations which we can use to properly define a coordinate point in any coordinate plane. So in this case, any value or any coordinate point given in x comma y, we could also found that same value by doing r times the cosine of theta and r times the sine of theta. The only difference is that this is in rectangular form. And now this is what we're going to be discussing today, which is this is something that we refer to as polar form. So let's get started. Now, like we just introduced our introduction question, we stated that we can represent any point in the Cartesian plane and what we call polar coordinate plane. And in order for us to properly define a position on a polar coordinate plane, we need two things. We need the directed distance, which we have defined previously as r, and the directed angle, which we have defined as theta. Because notice that that's how we define our polar coordinate point. R cosine gives you x, r sine gives you y. And in order for you to find this value, you need the value of r and the angle. And the same goes for y. So these are two ideas, or these are two information that we need in order for us to define points in a polar coordinate system. Now, notice that this system is going to look a little bit different because now there is no x, there is no y. We want to come up with a system that only relates to distance and angle. And here it's a small example of how our system is going to look like. So this is what we're going to refer to as the polar coordinate system. And this polar coordinate system, notice that is composed of two values, r and theta, where we call that r is the directed distance and theta is the directed angle. So let's start by plugging in some locations on this polycoordinate system. So let's start by representing the following points. So let's plot this value, point A, on my polycoordinate system. Now in my polycoordinate system, my first location will be of a placeholder for r, and my second location will be a placeholder for theta. Where if we take a look at our circle, every single complete circle you can think about as just having a r distance. So this circle is just a circle where all points are 1 unit away from the origin. This circle is composed of points that are 2 units away from the origin. This circle is made of a circle whose points are 3 units and 4 units. So now we want to come up with a point that is 2 units away from the origin and also has an angle of pi over 3. So we're going to take a look at a circle which has a radius of 2. So that will direct the point of r being equivalent to 2. And it's not just that we're just going to choose a random point. We want to choose a point that is 2 units away and also has an angular distance of pi over 3. And that will be exactly at this point. Because notice that exactly at this point, you're 2 units away from the origin, because you're on the second circle. And also, if you take a look at your angular distance from this point all the way to here, notice that you're traveling pi over 3 units from the origin. So that's how we're going to be defining our polycoordinate points. Let's take a look at another one. So let me just label this correctly. So this is A. Let's take a look at the next one. We want to take a look at a circle whose radius is 3. So let me actually do this in a different color. We're going to do B now, where r is 3. So we're going to take a look at a circle whose radius is 3. And now where am I going to put my point in the radius of 3? We're going to put our point exactly where my angular distance is negative pi over 6. But notice that all angles are always positive. So remember that if we go counterclockwise, my angles are positive. And if we go clockwise, my angles are negative. So pi over 6 is about 30 degrees. So we're going to take a look at a circle that is 1, 2, 3 points away and also has a negative pi over 6 angular distance from the origin. So now this is where my location for B is going to be located. Let's plot some more. Let's take a look at point C. We want to take a look at our radius of 6, which unfortunately only goes up to 4. So let me just redo my circles. So now we're back. So we want to take a look at a point which is 6 units away from the origin and also has an angular distance of pi. So we're going to take a look at points which are on the radius of 6. And now we're just going to travel to where my angular distance is pi. From here all the way to here, that's pi degrees. It's a point that is pi degrees angular distance, and it's also 6 units away from the origin. So the last point that I do want to discuss is point D, which notice that point D now has a radius, not a radius, has a value of r, or the directed distance of being a negative value, and it has an angular distance of 7 pi over 4. So when your radius is negative, this is how you want to look at it. Well, first, let's identify the angular distance, 7 pi over 4, which is about right here. This is 7 pi over 4. And since I'm going to be looking at the negative directed distance, what I'm going to do, I'm going to extend this line, which we will use for 7 pi over 4. So let me just extend this line. And extend this line on both directions. So if I would extend it, notice that this is a point that is between those two, 11 pi over 6 and 5 pi over 3. So if I would extend it, I will be using the line that is between those 2 points over here. So this green line, it's a straight line that still uses the angle of 7 pi over 4. But since I want to go into the negative direction, I'm not going to plot my point going 1, 2, 3 units against 7 pi over 4. I'm actually going to go 1, 2, 3 units on the opposite direction. So let me explain this one more time. So 7 pi over 4 is this green line. I'm going to take a look at its angle, and I'm just going to extend its line. But since my directed distance is of a negative direction, I'm not gonna count towards 7 pi over 4. I'm not going 1, 2, 3 units towards 7 pi over 4. I'm actually going 1, 2, 3 units away from 7 pi over 4. And now, I guess, let me just erase this line because it's not really needed. Oops, I guess I should erase that one at the end. So there it is. These are the locations of those 3 coordinate points. Now let's take a look at example 2 now, because it says plot the following polar coordinate points and answer the following questions. So let's choose some points. Let's take a look at A. If we want to plot A, we want to take a look at a unit circle that is 3 units away, but now notice that we're using negative 3 pi over 4. Well, 3 pi over 4, that's 90 plus 45, which is about 135, or with it's 135. So definitely negative 3 pi over 4, that's negative 135. So instead of counting 135 degrees toward on a positive direction, I'm just going to count them in negative direction. So that's 90 plus 45. And I want to make sure that I'm just 3 units away. So 1, 2, 3. So this is where my point A will be located at. Because notice that we're going 135 degrees in a clockwise directions and 3 units, 1, 2, 3 units away from the origin. And now if we take a look at point B, notice that it is essentially the same point. It is the same point as A, 3 comma, negative 3 pi over 4. But now we want to do, once we reach this specific point, we want to go 2 pi. So if we travel 2 pi, we're going to get the same point. So this is the same location for B as well. And now to plot C. Let me start by looking at its angle. Negative 3 pi over 4, that's exactly this, a negative 135 degrees. Now if I subtract a pi, I'm subtracting 180 degrees. So once I have traveled negative 135, I want to go 180 degrees in the opposite direction. So that's going to land me exactly right here. And now let's pay attention to the value of r. R is negative 3. So we're not going to go 1, 2, 3 units on this direction. We're actually going to go 1, 2, 3 units on the opposite direction, which notice that we're landing on the same point. And lastly, for example, D. Same idea, we're going to start with the same. Negative 3 pi over 4, that's negative 135. Now I want to add pi degrees, so I'm now just going to go in this direction. I'm going to go on this opposite direction, which I'm going to land right here. And now we're going to go negative, or r to have a value of negative 3. So we're not going to go towards the point, but we're going to go against the point. And we actually have the same location. So now notice that there are 4 different ways that we can represent the same location. Now let's try to answer some of these questions, which all refer to example 2 here. So is there any relationship between the given points, which is A, B, C, D? Well, notice that there's a big relationship between all those points. And that is that all those points have the same location. All these points, A, B, C, and D, they all have this location right here. So now the following, it says, do points in a polar coordinate plane have a unique representation? In this case, no, because we have just shown that this same point right here, there are 4 different ways that we can represent the same location. And there's even more. But we just decided to just do 4 because that would be just too much. So when it comes to polar coordinates, there are different ways that we can represent the same location. And now, is it possible for us to come up with the general form for polar coordinates that will represent the same point? Because notice that we kind of use the same examples right here. Notice that we have almost the same combination here. So can we just generalize this? Can we just generalize this to say, look, this is just the general form to represent the same location. And the general form to represent the same location, it's as follows. Well, first we need to define a point. So let's assume that if we have a point, which again, any point will be given in the form r comma pi, then the following will have the same location. Well, I know that if we got a coordinate point and I add 2 pi, I'm going to get the same location, which is exactly what we did between example A and B. The only difference between A and B was that I just added 2 pi. In other words, I just went a full circle. So that's another way to represent the same point. Also, another way that we could represent the same point is by taking the original point and changing the value to negative r and subtract the pi. And that's exactly what we did with point C. If you take a look at A, if I change the value of r to be negative 3 and I subtracted a pi, notice that we just shown that it's exactly the same point. And also, in addition, another way that we could represent the same point is by still changing the value of r, but now we're going to add a pi. So given any point, any polar coordinate point, I would have got the same location if I do any of these 3 combinations. Now, let's actually dive deeper into the actual main idea for this lesson. So what we have discussed so far is how do we understand the polar coordinate system and how can we plot points in the coordinate system, in the polar coordinate system. But now, is there a way to go back and forward between them two? Because we've just shown that a point x comma y can be represented in polar form. So does that mean that polar form coordinate points can also be represented in rectangular form or x comma y? And yes, we can go back and forward between them too. So the polar coordinates, which it will always be represented as r comma theta, are related to the rectangular coordinates x comma y as follows. In order for us to define a point in a polar coordinate system, so for polar, we need an r and a theta. And for rectangular, we define as x comma y. So if you've been given a point in polar coordinates and you want to represent that point in rectangular form, so we're going to use what we just discovered in our introduction, where the x part of the rectangular form is going to be r cosine, and the y part is going to be defined as r sine. Now, if we want to go between rectangular to polar form, we need to know the value of r and theta. In order for us to get r, we have this expression, that we have this equation we which have used before, which also can be represented as r being the square root of x squared plus y squared, which is just the distance formula from the origin. And the theta, we're going to get it from the tangent value. So this is how we can go back and forth between them two. If you've been given a polar coordinate and you want to go into rectangular, then we use this conversion. And if you've been given a rectangular and you want to define it as polar, then we use this conversion. So let's do 2 examples. Under example 3, it says, convert the point 2 comma pi to rectangular coordinates. So for rectangular, we need an x and a y. And notice that the way that we've been given here, this is my value of r and this is my value of theta. So therefore, x, I know that that's represented as r cosine of theta. So therefore, my x value, it will be 2 cosine of pi. And then cosine of pi, that's just equivalent to -1. So therefore, x has a value of -2. So now we know what x is. All we need is just a y. But remember that y is defined as sine of theta. So therefore, we're going to have 2 times the sine of pi. Because all I'm doing, I'm getting my r, I'm plugging it in here. I'm getting my theta, and I'm plugging it here. But sine of pi is 0. So now we know that y is 0. So therefore, the rectangular form, or the coordinates for the rectangular point, it is of a value of -2 comma 0. So the polar coordinate point 2 comma pi in polar coordinate, it's equivalent to the rectangular form at -2 comma 0. One way to visualize this is if I would have plotted the point when x is -2, if I would have plotted this point, which is the rectangular form, notice that this point can also be seen as an angle of pi, which is 2 units away from the circle, which is exactly what we wanted to graph here. So let's do one more example. Now let's try to convert the point -1 comma 1 into polar coordinates. So therefore, I want to use this conversion. So in order for me to find the polar coordinates, I need my value of r and I need my value of theta. So let's start by defining r. So notice that here r, it's equivalent to the square root of x squared plus y squared. But notice that -1 is my x and 1 is my y. So therefore, my value of r is just -1 squared plus 1 squared, which is just the square root of 2. So I know my value of r. The only thing that we're missing is the value of my theta. And for theta, we gotta be a little bit careful here now. Let's visualize where my point is located. -1 comma 1 is exactly here. Therefore, I can think about this as if it was some kind of a right triangle. And my value of theta, or the theta that I'm looking for, is all this. If I want to use this conversion, the tangent of theta being equivalent of y over x, this is only going to give me the angle of this circle. I'm sorry, of this triangle right here. So we gotta be careful about how we want to interpret the following result. So if we want to use this conversion, so I know that the tangent of my angle it's equivalent to y over x. So therefore, the tangent of the angle, y is 1, x is -1. Therefore, my angle is the inverse tangent of -1. And if we would use our unit circle, we would have seen that now my theta has a value of -pi/4, which is -45 degrees. But I'm going to keep it all in pi. So what we have shown is that this angle right here is -45 degrees. So just 45 degrees. Doesn't really matter too much if it's positive or negative at this point. All I know is that this is 45 degrees. But I know that my point, or the actual data that I want to use for my coordinate system, should be what is on green. So notice that what is on green, one way to think about it is is going to be pi minus the angle that we got on red. So therefore, the angle that I'll be using is going to be pi minus pi over 4. Because if I want to use a pi, it's this whole thing. From the positive x coordinate to the negative x coordinate, that's a full pi. So therefore, I want to take away this much in order for me to get the green distance. So therefore, I'm going to end up with a value of 3 pi over 4. So now I have enough information. From my coordinate system now, let me just move that in here. Now, my polar coordinate it's a value of r being square root of 2 and theta being 3 pi over 4.